Good morning, afternoon, just about everything else. Everybody, my name is Josh. I'm here for our virtual tour of outer space. Now, virtual tour of outer space is a program we've been doing weekly, behind our software, giving us a chance to send out into the universe a tour of our own solar system and beyond. Now, this is a program sent out through the Morrison Planetarium and through our partners over at OpenSpace on YouTube. So if you're watching from YouTube, hi everyone. If you want to find out more about some of the programs we're doing, check out our Facebook account, and you can see all the stuff we do every week, targeting a wide variety of interest groups and age levels. There's some really cool stuff to see. But for today, we are doing kind of a different sort of program because this is one not guided by me, guided by you, the viewer. So if there is a place in our solar system or beyond our solar system that you think would be excellent to check out, by all means, throw it in our comments, in our chat. And my producer, Mary, will pass it along if she thinks it's a really cool opportunity for us to check stuff out. And I'd be happy to fly you there and tell you whatever I can think of about the object in question. So we began our chat, or I should say our show, with a very interesting object, one we've visited several times and one people are always keen to view. This is the surface of Pluto. Now, we are seeing Pluto in the OpenSpace software. Now, OpenSpace is planetarium software. It's what we use to present some of the shows in our dome, planetarium, the Morrison. But it's actually kind of a special sort of software because it is open source, and this is something that you yourself can download and use. I suppose you could download some of the other softwares, but the companies charge a lot to use them, and this is completely free. It's based on NASA imagery, as well as planetary images taken from other partner space institutions, but this is all using stuff that is available to you, and because of that, it is a free product. So I would encourage any of you who are tech savvy or space obsessed and who really want to check out this kind of imagery for yourselves. We have been checking out the icy dragon's teeth or penitence of Pluto, which is just a really cool way to start a program. So it looks like we had some requests. I can see one coming in from, let's see, Virginia wants to go check out Saturn. I think that is a great way to start a program as well. Now, zooming away from Pluto, I'm going to call attention to one thing, two things actually. Number one, it looks like someone took a bite out of Pluto right there. That's where one camera image ends, one picture ends, and another picture begins. So there's not actually a weird rectangular slice taken out of Pluto. But secondly, when you look at Pluto, you can see sort of that, I don't know, grayish dun color. Almost brown, not quite. Some photos show it as a little bit more pink with some concentrated blues in there. But this is a subdued color image. It's maybe not exactly what we'd see with our eyes at Pluto, but part of that is also the lighting at Pluto is not the same kind of vivid, bright lighting we're used to here on planet Earth, which is so much closer to the sun. When we zoom out to Saturn, you're going to see a very vividly bright object, a beautiful object. But think hard before we get there. What color is Saturn? Now, I'm not going to tell you anything until we get there. As we are zooming in, though, think about that idea. What color is Saturn? I'm zooming on the wrong window. That would have taken a long time. Here we go. So as we get closer and closer, from this side, Saturn's black. Bet you never thought of a black Saturn when you're thinking of Saturn's color. When we think about color, we are thinking about the presence of light. So light from the sun hits Saturn, bounces off, giving us whatever colors are reflected by the surface of Saturn. Whatever colors of light are absorbed, we just don't see. That's the nature of how we see color. When you look at those rings, again, they don't make light. We're seeing light from the sun bounce off of them. But the light that's bouncing off has interesting kind of yellows, maybe some darker hues mixed in. Well, they're probably a little lighter, a little whiter, a little icier because we are seeing an icy surface. When you look at Saturn, though, we get an interesting blend of colors. Now, there is kind of that same dun brownish color, but there's also, I would say, quite a lot of yellow. And if you look around at some of the beautiful up-close Cassini photos, something really shocking comes out. The presence of blues and whites inside the atmosphere of Saturn. I'm not 100% sure about the chemical makeup or the change that makes those blue and white clouds so vivid, but in some of those close-up photos, they really are. Now, another interesting feature of the clouds of Saturn you can see down at the pole, the infamous hexagon. I didn't know this was as big a hit as it is, but we've had a lot of people asking about the hexagon, so I thought I would point it out. If you're not too familiar with geometrical terms, hexa is a 6-sided shape. So we can see 1, 2, 3, 4, 5, 6 sides right here. This is a pretty cool thing. Now, currently, scientists can observe this. We had the Cassini mission going around for long enough to show us this is a stable feature. It's not like it just appeared like that one day. But this 6-sided shape is still an elusive thing. We're trying to understand exactly how and why that has formed in the clouds of Saturn. Now, soon we might be sending some missions back to Saturn, but they're actually not going to be focusing on the planet itself. The next mission to the Saturn system is likely going to be focusing on one of the moons of Saturn. Now, this moon we were talking about earlier today, so I've been thinking about it a lot, is Titan. Titan is an absolutely fascinating place. If I were to tell you that there's something in our solar system that is bigger than Mercury, almost as big as Mars, just not quite, has a thick nitrogen atmosphere and liquid on the surface, that sounds like Earth 2.0, right? The best place to go. Well, that is Titan. When we think about Titan, it is a place that is in so many ways so similar to Earth. There's a ton we have in common with it. But this atmosphere, even though it's made of nitrogen primarily, is so thick, so hazy, we can't actually see the surface. If we wanted to get a good view, we really have to get up close and personal and drop something down, like we did with the Huygens probe, or else use a different color of light. Because the clouds look sort of orangey to us, that's the color that's reflecting off of them, we need something that would go through those clouds, bounce off the surface, and come back to that probe, so we use radar. The radar mapping of Titan shows us these dark regions, which are by and large what we call the mare, or oceans. On the moon, we call the dark spots mare, but that's just hardened lava. Here, these are lacunae, are the lakes of the surface. And some of them, I believe, have analogs here on the Great Lakes of planet Earth in terms of about their volume. But some of these are actually named after, I believe, sea monsters, which is just about the coolest things ever. So there's the Kraken lake on the surface of Titan, and that's just super cool. I saw a cool question pop up from Natalie that was, do all planets have atmospheres? Not all of the planets in our system have atmospheres, depending on what you call an atmosphere. I would say that because when we look at Saturn, its outer layers are gas. I have a very easy time saying that that is an atmosphere around that. Titan has an atmosphere, even though it's not a planet. But when we travel to a place like Mercury, there's no appreciable atmosphere. Now, I can hear one of my friends who I'm sure is going to say, well, actually, they have detected a few atoms of gas around Mercury. But that is at best you could call maybe an exosphere, because the atoms are actively escaping Mercury. So I would not say that Mercury has an atmosphere, and I can actually prove that to you with our software by crashing into Mercury. That's not what I meant to do. By looking at Mercury from the dark side. If we were to do this with planet Earth or Venus, we would see the atmosphere bending around that edge, because the folks at OpenSpace have worked very hard to make sure that we are accurately modeling atmospheric limbs. Light from the sun just stops, and that's telling us that around the edge of Mercury there is no atmosphere to bend the light. A sunset on Mercury would just be the sun getting closer and closer to the horizon, then disappearing. You wouldn't get the cool colors or cloud effects that we do here on our planet. So because of Mercury, I can't say all the planets have atmospheres. Mercury is the exception to that rule. But if we think through it, Mercury, no atmosphere. Venus has an atmosphere. Earth has an atmosphere. Mars has an atmosphere. Jupiter has an atmosphere for some values of atmosphere. Same thing with Saturn. Uranus and Neptune, they have atmospheres too. And heck, if you threw Pluto in, Pluto has an atmosphere. Now, it's not a huge atmosphere compared to us, but we wanted to know from Virginia, could we live on Titan? There are certainly some people who think we should go send explorers to Titan, like the Dragonfly mission, but for human beings, we're a little bit less tough than our robots. So if we sent a human being to go live on Titan, they would get very chilly very fast, because the biggest hurdle to human habitation, I would say, would be temperature. Now, the air itself is pretty toxic too, but temperature would get you pretty quickly. However, in kind of a grim turn, I can tell you, we often joke about this. If you were to take a vacation on any world in our solar system without the benefit of a spacesuit, your vacation would probably be the longest on Titan. because it takes you a couple seconds for cold to get you. Whereas most of our other planets, your vacation would be a whole lot shorter. Okay, so we have a couple more questions coming in. Let's see. Bree asked, the Girl Scouts of Troop 31011 want to see a black hole. Well, I hate to say it, seeing a black hole is always a tough thing to do. But I think if we point our software in the right direction, I can at least show you where a black hole is, and I hope that's an okay substitute. I mean, nothing would be as cool as seeing a black hole, I guess I have to say. But this is still, I think, one of my favorite things in our sky. So how do I know where I'm looking? I'm going to find some good constellations to show me the right way to go. And I'm going to start off with my buddy Scorpius over here. If you look at, there's a little umbrella of stars and nice chain through here. This is the scorpion's tail. That's the heart of the scorpion. We call that Antares. And as we go through, you can see the sting of the scorpion. Some people might call that Maui's fishhook. So if I can find the tail of Scorpius, then I can see right over here is Sagittarius the Archer. Now, if you find Sagittarius the Archer and Scorpius, right between them is this big, dark, cloudy region. That is our Milky Way, and that dark region is actually the thickest, widest part of the Milky Way. If you were to measure it with your fingers, you would see that it's ever so slightly thicker than any other part. Well, guess what? That's us looking away from the outside of our Milky Way towards the middle of our Milky Way. And if we look towards the center of our galaxy, we actually get to see something absolutely fascinating, beyond awesome. We are going to see in the direction of Sagittarius A star. That's kind of a funny name, but Sagittarius A star is the name of the not just black hole, but super massive black hole that lives way down there in the center of our barred spiral galaxy. Now, if you want to hear a great explanation of how we understand the shape of our galaxy, I would recommend tuning into last week's Cosmic Conversation, where our very own Rook Fitz gave a great description of how we come to understand the shape of a galaxy that we live inside. As kind of a different analogy, I always like saying to folks, we eventually figured out the shape of the United States, even though no one had ever been above the United States, but we did it by very carefully examining the structures we could see to understand better the shape of our continent as a whole. No one had been to space, and we still had pretty good maps of the United States. So by piecing together the little bits of information we do have, we've come to understand the shape of our galaxy. And we've been watching some of the stars way down here in this bright central region. Some of those stars are moving incredibly fast. And when they're moving fast, it's because they're being pulled by something's gravitational influence. So the faster you move, the stronger the gravitational influence. These objects are also getting very close to the thing that's pulling them, and they're not bumping into it. And that tells us that the thing that's pulling them is very, very small. And the stars themselves shine light, but the thing they're orbiting doesn't. So when we added up those pieces of evidence, the things we can observe, we came to the conclusion that there's something very heavy, very dark, and very small in the middle of our galaxy, and that tells us that we are seeing a supermassive black hole. So when I talk about this, Natalie wanted to know, is this the only black hole in the center of our galaxy? Turns out if you have two black holes and they're close enough together, you'll eventually have one black hole. We call it a black hole merger. It's possible. There are some ideas that this black hole helped form our galaxy, and there's also some people that say as our galaxy formed, it made this black hole. I think there's a lot of ideas going back and forth. According to Karen, how did this galaxy form? There's not broad consensus about the details, but we do say that there was at one point in the Milky Way's ancient history what we call a dark matter concentration. And the dark matter made observable, regular, baryonic matter, we call it, like you and me, pull together a little bit. And in that pulling together of the regular matter, our galaxy formed. But it's been a relatively violent age. Like, we have not just existed by ourselves peacefully. There have been dwarf galaxies, smaller galaxies orbiting our own that have been pulled in and probably pulled apart. Now, there's a couple papers being presented this week at AAS, the American Astronomical Society, talking about what's called the Sagittarius stream. And I personally am looking forward to this Friday's conversation because I love galaxies and galaxy shapes. And we're going to be hearing from our very own Ryan Wyatt, and one of his friends who's been at AAS, I think it's Carolyn Peterson, is going to tell us all about the new discoveries coming about the Sagittarius stream moving through our galaxy and what it teaches us about the galaxy's formation as a whole. I got distracted though, so if you want to check out the supermassive black hole Sagittarius A star way down there in the center, you can actually look at some really cool telescope images of the stars going around it. And for a really close match, even though it's not in our galaxy, there was the Event Horizon Telescope took a photo of a supermassive black hole in the middle of a galaxy. And that would be a pretty good guess at what our black hole looks like, even though it wasn't taken of our own black hole. So with that, I'm heading back to a little bit more close-in perspective. I love the galaxy. I could spend the whole show talking about the galaxy, but last week I flew people out to the edge of the universe, so I feel the need to stay a little closer to home this week. Let's see if there are any other questions coming in. Io or Europa, great idea, Sam. That sounds like a perfect Earth analog kind of thing to do. Why don't we do both? Okay, so we are currently targeted Europa. You'd never know it because we're still like a light year's distance away. But as we zoom in, we are going to go see the surface of Io up close. Now, we were in a conversation about this a while ago. Is it Io or Io? And if you say them fast enough, it sounds like you're doing Old MacDonald. But if you're thinking specifically about the character from Greek mythology, I think a lot of people would prefer the Io pronunciation. For the astronomical object, I think Io is the one that a lot of American astronomers at least use. When you look down at the surface of Io, it is a fascinating contrast. This looks like, well, really nothing else in the solar system. I guess maybe some of the cloud patterns on Venus, but the big difference is Venus is an atmosphere. There's little to no atmosphere on Io. Now, what we're seeing, this mottled wavy yellows and whites, are evidence of volcanic plains. When a volcano goes off on Io, it's a very different process than what we have here on Earth. What we have here on Earth is largely dictated by the interaction of explosion, the force coming up from inside the very energetic environment below the surface of Earth. And then as soon as it reaches the surface, it's dictated by Earth's gravity and by Earth's atmosphere. So the volcano goes off, material is flung up into the air, but air, keep in mind, and as it's flying around, it's going to cool very quickly before landing back on the surface, again dictated by gravity. Io is orbiting Jupiter as a moon. It's one of the 4 Galilean moons. Thanks for the clarifying question, Amy. But when we look at Io, it's got a much lower coefficient of gravity as a very small object, or at least smaller than Earth. The same explosion is going to send things farther away, and there's no air to provide resistance. So things aren't going to slow down. They're just going to travel in whatever direction they're blasted, minus the acceleration due to gravity. Now, with those factors, we get completely different kinds of volcanism on Io. But at the same time, we see similar-ish structures to what we see on Earth. And that really helps us understand geology and volcanoes in a new sort of way. That, to me, is one of the coolest things about studying a similar structure in a different environment, because you get a much better understanding of what's going on for that phenomenon. Karen wants to know, are there any other moons that have volcanoes? Absolutely. Our own moon would be a great example of lunar volcanism. But we see similar kinds of structures on Enceladus in that it has cryovolcanoes. We've actually seen a cryovolcano on a dwarf planet that is Ceres. And if we go right next door to Europa, we actually get to see cryovolcanoes as well. A rocky volcano is where you have liquid rock moving through solid rock and making a volcano of liquid and solid rock. When you get to Europa, you've got liquid water moving through solid water to explode and create a volcano of liquid and solid water. So you have a very analogous system. Is even what we think of as like subduction zones happening on the surface of Europa, where one chunk of crust is sinking below another and forming ridges of volcanoes. The surface of Europa is fascinating, wonderful, and beautiful. And I just love when you see one of these high resolution patches to dive in as close as you can and just see the amazing crisscrossing, almost vein-like structures. And check this thing out. These super wide regions, we found out that's where a crack has been happening, and as the surface gets pulled apart, slush moves up underneath and hardens again. That's almost the exact same process as we see inside the divergent plate boundaries, where new oceanic crust is being made, like right in the middle of the Atlantic. I think it's the mid-Atlantic ridge. In fact, I'm sure it has to be in the middle of the Atlantic because its name means in the middle of the Atlantic ridge. But when you look at these features, these kind of spots where new crust is being made, it also reminds you that as new crust is being made, Europa is not just swelling up as a planet or a moon. Some crust has to be deleted elsewhere, and that's where you get that subduction and the formation of these volcanoes, much like we have here on Earth. But now I'm thinking about our moon, so I'm going to head to our moon, unless we have another question pop up. Boo, boo, boo. Heading out this way. So as we head into the inner part of our solar system, we are getting a lot closer to the sun, and as we get closer to the sun, liquid water gets a little bit more challenging. And you get light shining down on the surface of a world like Earth. We absorb a lot of it. That heats up the surface, so we get liquid water. As we dive in towards the moon, I don't know if you've seen the moon the past few days. It's just been a teeny tiny crescent. And this software is actually showing us the accurate position of the moon, so we see the moon lit up. But does that look like the moon you're used to? Probably not. This is the far side of the moon. So the far side of the moon is pretty much entirely illuminated, showing us the surface of the moon we don't often see. If we want to see our familiar surface of the moon, we go to this side and immediately run into a big problem. We have nighttime. So in order to turn nighttime off on the moon, I'm going to invoke a little bit of planetarium magic, which is not something we are used to seeing in real life. So looking around here, you can see all sorts of cool stuff around on the surface of the moon. I'm going to show you, I think, Brian Day taught me how to find this structure. So I'm going to do my very best to not disappoint him and try and zoom us in. I think it's right up here. So the way I find this is to find my number one most favoritist moon feature, which is the Reinhard Gamma right there. And then go northwise from that, which is actually this direction right now, and then find what I call the Harry Potter feature. Why do we call it that? It's got two little round glasses and a lightning bolt on his forehead. So if you can find that, you zoom in, and right over here, there's tons of volcanoes. I know what you're thinking, Josh, those look nothing like the volcanoes on Europa or the volcanoes on Earth. How do you know there's volcanoes there? The real answer is I'm guessing, because that's where I remember them being. But I'm going to see if I can do you one better. And we are going to go into the awesome OpenSpace software and see if I can show you one of the layers that gives us... My dog is very unhappy. I'm sorry about this. Okay. I'm sure someone walked by the front of our house. He really hates when that happens. So if you spend enough time on here, you would find there's one of these gives you a great relief. I'm worried I don't have it loaded, and I would spend the whole time looking for something that's not there. But you can see the actual like black and white height mapping of what's going on. Oh, it just took a second to load. There we go. My dog's name is Asher. It's short for Asher Bonapal. Thanks for asking, Tanya. But if you look around here, you can start to see those bumps popping out. Those bumps, those elevation changes, are showing you where we have the volcanoes on the surface of the moon. Now, this, I think, is just such a cool way of showing off the elevation change on the moon. We think of the moon as relatively flat, but really that's absolutely not the case. We've got huge mountain ranges. If I recall correctly from Bing Kwok, one of my coworkers, there's actually a taller mountain on the surface of the moon than there is on planet Earth, and I believe it's right around here. So why do these dark areas look so smooth in comparison to the light areas of the moon? Well, I'll give you the really lame answer. It's because they're actually quite smooth in relation to the light areas of the moon, but that's a lame answer. Those are where we think lava pooled on the surface long ago and covered up any bumps that were there. So when the lava spread out, anything that was a minor variation just disappears. When we look at the light areas, they're super bumpy because they're what we call the highlands. They are literally just higher up, so lava didn't pool there so much. Now here's the really cool thing. We're going to poke around here. Look how big and smooth and round this is. Probably an ancient crater where something smashed into the surface of the moon, lava flowed up and covered it up. When you look over here, this is that little light region of the moon surrounded by all the dark stuff. And down here, you just see tons and tons of craters. Now let's try this. We're going to go over here to the far side of the moon. Remember where we started off before? Here's where some of the highest elevation parts of the moon are. And you'll notice that there's like no broad flat areas. This is just crater on top of crater on top of crater. In this case, literally, 1 crater, 2 craters, 3 craters, 4 craters all on top of each other. That's really exceptional seeming feature. Also, check out how tall this is. It actually went to white in the software. This must be like one of the highest elevation parts of the moon, on this part at least. Oh man, now you can see down here by the South Pole Aitken Basin. If I had to guess, this is it. It's one of the biggest craters in our solar system, and we think this is a single impact site. An absolutely gigantic structure smashed in there. And that to me is just so cool. Think about the history of our solar system. Something big enough to really make a bad day on Earth smashed into the moon instead of us. So how is a crater made? Basically a falling object. It could be almost any kind of falling object. Something from space comes down to the surface of whatever world it's attracted to and smashes into it. Now, sometimes the gravitational pull of the object is inconsequential because things traveling through space can be going at very high speeds. Things like meteors are things usually under 10 meters across, so they don't make that big an impact unless they're going really, really fast. Larger things like asteroids or comets are often what we think of creating the really big impacts in our solar system. When we're thinking about asteroids or comets, the more dangerous of the two, I would largely say, is asteroids. And why is that? Comets, because asteroids are hanging out in the belt of our solar system. They've got a pretty predictable orbit. They're generally traveling in the same direction as planets. Not that big a deal. But when you look at a comet, they can be traveling at incredible speeds as they get closer and closer to the sun. So a comet hitting your planet is an absolutely horrible day. It would probably form a crater and make life not that fun if it hit planet Earth. So no one has been to the south side of the moon. We have landed on the southern hemisphere, I guess, Sharada. But we haven't gone to the South Pole, but that's actually one of the spots that we would love to send some explorers, I think probably robotic, sometime soon, because we are pretty sure there is ice on the surface of that moon. Our moon, I should say. And with that, I think we are very close to the end of the program, but let's see. I'm looking around if there's any other. What is the rotational period of the moon? The rotational period of the moon is the exact same as its orbit, Chantrell, so that is a month. What we think of as a month here on Earth is a day on the moon, because that's how long it takes for it to spin with respect to the sun, or just about. And it's also how long it takes to complete an orbit around the center of its orbit. So if you line those two ideas up, I've got a really tough question for you. What is a year on the moon? I'm not going to tell you the answer. I'm going to leave that. Maybe we'll think about it. And next week, I think Ethan, Scardina, or Mary is going to be in the pilot's booth. So you can ask them that super tough question and make their lives harder. So with that, I think we are good to go. Thank you all for dropping by and joining me for our virtual tour of outer space. If you came up with a question at the very end and I didn't have a chance to answer it, by all means, save it up, ask it next week, or leave it in the chat, and we will do our best to comb through later and answer some of them. For myself and for OpenSpace, we so appreciate you tuning in and joining us for this. It's a really fun program for us. If you feel like downloading OpenSpace, head to the OpenSpaceProject.com. It is a great resource. You can also join folks on the different user groups. And if you've got questions or answers, I'm sure they would love to hear. But on behalf of myself, Morrison Planetarium, and everybody else, thank you all for joining us and have a wonderful rest of your day.